The objective of this lab is to analyze the motion of an object that has constant velocity using tracker to capture the motion of a real-life object, and then model it using Newton's second law of motion on VPython. The real-life object will be analyzed to see if there are any inconsistencies or deviations from the model based on this physical law. The object used in this experiment is a size 5 soccer ball that is rolling across the floor in my dorm. The ball is centered at the origin based on my tracker representation and moves in the positive x direction as indicated. Tracker is calibrated based on the diameter of the soccer ball being 0.22 meters. Now, in order for the ball to be rolling at a constant velocity, Newton's second law states that the net forces on the ball must be 0. So in the y direction there is the force of gravity that is acting on the ball, but the floor is counteracting this force with equal magnitude but in the opposite direction. Therefore, the net force in the y direction is 0. In the x direction, the ball is not experiencing any push force in the positive x direction, and the air resistance and friction on the ball are so small that they are not noticeable over this time period. Therefore, the ball can be considered to have no forces acting in the x directions as well. The ball was not moving in the z direction, and no forces were acting on the ball in this direction, so therefore it also has a net force of 0 in this direction. Overall, the net force on the ball is made up of these three directional force components and is equal to 0. This clip shows the ball moving at a constant velocity using the tracker software to analyze the location of the ball at each frame. As it was moving, this graph is showing the ball's position in meters based on the time in seconds. After doing some quick calculations seen, the ball's initial velocity based off of the initial and second location is 1.06 meters per second. The ball was in motion for a total of 1.1 seconds. Using VPython, Newton's second law was used to calculate the object's location based on initial velocity and the forces acting on the ball. Since the ball is not experiencing any forces, the model will move at a constant velocity. Before running these lines, however, the initial velocity, position, and time of the ball must be inputted in order for the Newton's second law to be carried out by the software. After plotting the motion of the ball in real life, indicated in blue, versus the motion of the model, indicated in red, the model actually underpredicted the final position of the ball. In order to fix this problem, I realized that the initial velocity of my ball may be higher than 1.06 meters per second, and that my calculations may be off just due to where I clicked on the position of the first point. So I chose to analyze the velocity of the ball using the positions of the ball at times 0.033 and 0.067 seconds. After doing the same calculation as earlier, the ball's initial velocity was calculated to be 1.09 meters per second. Once again, Newton's second law is used in the VPython code, and there are no forces acting on the ball. The motion of the ball is seen in this computational model. Unlike the real-life tracker depiction of the motion of the ball, the computational model provides a perfectly straight line with a slope of 1.09 meters per second on the graph of position versus time. Again, in order for Newton's second law to work properly in VPython, the ball's initial position, velocity, and time are used. The plots of the experimental position and the model's position are much closer to the same exact graph, so we can say that the soccer ball was moving at a velocity of close to 1.09 meters per second in the positive x direction. Overall, Newton's second law predicted the motion of the soccer ball very well once the initial velocity of the ball was correctly found.